My name's Jason, and I've been your professor for the last 10 weeks. It's a little weird that this is the first time we're actually seeing each other, but it's been, things have been weird. So I hope everyone's doing well. Today we're going to do a review of our upcoming final exam for this week. What I wanted to do was address some of the weak areas I've seen on the quizzes up to this point, along with covering a couple of clarifying items and talk about what to expect from the final exam. Hopefully you've been following my announcements and are staying up to date on what to expect. So let's jump in with fission product barriers. On your first quiz, I'm looking at your quiz statistics here. 62% of you answered the question, which of the following are fission product barriers, correctly. So I wanted to go through that list and talk about what a fission product barrier question might look like. There are 6 fission product barriers. Sort of. It depends on the context. When we talk about physically what are the barriers, those are the 6. Now later on in module 2 or 3, we talked about emergency classification levels. And in those emergency classification levels, they lump some of those together and they only consider 3. So let's talk about the 6 fission product barriers. We have the fuel pellet. That's where it all starts. That's where the uranium's at. The uranium-niobium mix in that little matrix, kind of a ceramic-ish thing. Then they're literally about that big. I know I'm not holding anything, but that's how big they are. And then, like the size of a pencil eraser. And if you pulled the pencil eraser out of a pencil, it's about the size of them. That's designed to retain most of the fission products. So when fission happens, a uranium atom absorbs a neutron. And to do that, that neutron has to be what we call a thermal energy. It has to be thermalized. And that's why we need the moderator. That's why the water's there to slow down the neutron that came from some other fission. That neutron bounces around in the water, off the water molecules. And just like playing pool, right? The cue ball bounces off another ball. That reaction takes away some of the cue ball's energy. And that cue ball eventually gets down to the energy level needed to be absorbed by another uranium atom. And when it does, all those protons and neutrons are unstable enough, and sometimes they're just unstable enough that one more person arriving at the party is what causes everything to go, and then it splits off. I'm talking too much about that process. Everything splits off. What's left, when that uranium atom breaks apart, you're left with other elements, like krypton and xenon. You see that often because those are some of the most damaging, some of the worst ones we can have. Anyway, those still should be right in that little fuel pellet. And that's the design of it, right? That's why we don't just put a lump of uranium. That's why we mix that uranium into this fuel pellet, into this ceramic-ish niobium matrix, so that it's all encased, hopefully forever. Now, some of that will come out, especially near the outer edges of the fuel pellet. But 99% of those fission products should stay in there. And so that's our first barrier. Now, what if some of that 1% that leaks out? Well, that's the next barrier, fuel cladding. The fuel cladding is designed to keep any of the leakage from those fuel pellets inside the fuel rod, especially the gaseous stuff and gaseous and non-gaseous. All the fission products are designed to stay inside the cladding, mostly in the fuel pellet, but like we said, some of it will come out. So right there, that should end. Like, there should never be an issue from that point on. However, nuclear reactors are finicky beasts, right? We're talking about high temperatures, we're talking about high flows. We have to maintain the core covered. We have to keep water on there, which is the moderator, which causes the fissions. I mean, it's a weird back and forth balance, right? We have to add the water to create the fissions, but then that creates the heat that needs the water. So we can't take away the water to stop the fissions once it's started, because then we're not able to remove the heat. Anyway, if we were to have an accident where for whatever reason some of the fuel became uncovered, where the temperatures got too high, We had a change in our boiling process, right? We never talked, this is our first talk. Through our course, you read about how the water covering the fuel, right? And then the boiling happens, and that boiling, those bubbles, leave the fuel cladding surface and transition to, they get carried away into the center of the coolant. Now at first, that coolant channel, those bubbles will collapse, right? Because it's below saturation. And then it's getting hotter. That heat is getting carried away from the wall of the fuel and into the bulk center of the coolant, and it's heating it up. But at first it's below saturation. Eventually, those bubbles start to come together. Once it's saturation, that center part of that coolant channel is boiling. It's vapor, it's all bubbles, right? And the bubbles leaving the fuel are building and building into that. And we're driving that flow with our recirc pumps, forcing that flow up past the fuel, carrying those bubbles away. And then eventually, if we heat up too much, we have too little flow, if our flow goes down too much, some of these balance things get out of whack. Eventually, that bulk boiling in the coolant, it grows so large that there's no water to carry the bubbles away from the cladding. And that's the departure from nuclear boiling, where those bubbles start to just stay right there on the fuel cladding, and then eventually this fuel cladding is dry, right? And that's dry out. So we've got a 12-foot long fuel channel, and so the bottom part is going to be covered with water below saturation. We want to maintain the bulk of that center bit saturated nucleate boiling. And then at the top part, yeah, it's okay to get some steam going to the fuel cladding near the top, because the way we design our fuel is such that a great deal of our uranium is going to be in the center of the channel. We design our fuel so that some of our fuel rods have dummy pins at the top, so there's not as much energy at the top and not as much energy at the bottom. Anyway, if we start to get that dry out condition and that cladding heats up, right, because the fission's still happening in the fuel, now it's going to slow down a little bit without that moderator out there, but below there you still got moderated fission happening, and those neutrons are still going up to these uranium atoms at thermal energies. Even if those uranium atoms up here there's no water, no moderator outside of the coolant channel. And that's where problems really start to happen, is at that boundary, right? Things really start to heat up. And you've read our ECCS design criteria. We have to maintain that cladding temperature below 2200 degrees Fahrenheit. We have zircaloy reaction issues. We have cracking. Eventually that fuel pellet can crack. And when that fuel pellet cracks, that releases fission products. And when the cladding's damaged, now there's fission products released into the coolant, into that channel. That's where problems really start to happen. In fact, that is the definition of core damage, when there's damage to the fuel. Because when fission products are released from the fuel and the cladding, that's core damage. And because that can get carried away to the primary coolant. Now, the primary coolant is another fission product barrier. So even if we have this bad stuff happen, all this water in our primary coolant system that's going through the core, goes out our steam lines, goes through the turbine and into our condenser, most of that should be, some of those fission products are water soluble, and they just get dispersed into that coolant system and they get cleaned out by our condensate demineralizers before the water goes back through the core again. And so we can clean up and prevent release of fission products that way. Now, some of those are going to be more gaseous and are going to eventually get out of the condenser. So we've talked about fuel pellet, we've talked about fuel cladding, we've talked about the primary coolant. The next one is the actual vessel itself, right? This is where this should keep everything together no matter what. This is the boundary that keeps the coolant inside the core. This is a difficult boundary to breach. We do have some intentional penetrations into that. We have to get the steam out of the reactor vessel, and it goes through the turbine to the condenser, and from the condenser we have to get those air and non-condensable gases out of the condenser, and those get released through the stack. So that's kind of the risk there with RPV and primary coolant boundary. All right, I've talked a lot about fuel pellet, fuel rod cladding, a little bit about the reactor coolant and the reactor vessel. I'm going to cut off about 5 minutes of my babbling. Just know that the last two are primary containment and secondary containment. You're welcome. What I would know is read through your notes, read through your text, and pay attention to how each one of those barriers prevents release of fission products. Think about your research on your projects and what barriers failed. That would be something if you were to answer a question using an example of, and when we studied, when you look at Davis-Besse, right, what did we almost have a failure of? When you look at 3 Mile Island, what did we have failures of and what didn't we have failures of? And despite what failures we had, what was significant and what was not significant? How come 3 Mile Island ultimately, from a release to the public perspective, wasn't a big issue? What worked here? So knowing those 6 is going to be important. Now, when we talk about emergency classification levels, they group some of them together. So we're really talking about, they're in emergency classification levels, they're talking about fuel as one, which for us is fuel pellets and the cladding. So if the fuel barrier breaks. The second one is the reactor vessel and primary coolant. Sometimes it's called the PCS boundary, primary coolant system, which includes the RPV. That's the second barrier. And then the third barrier is containment, and they lump primary and secondary containment together for those. So from an emergency action classification perspective, there's 3. Fuel, primary coolant system, and containment. So some of you had responded on the quiz that the reactor protection system was a fission product barrier. Let's talk about what reactor protection system is. Reactor protection system is 2 things in a boiling water reactor power plant. On one side, it's a logic system. So we're going to talk about logic systems next, and that's the logic system that drives our reactor scram actuation. The other side of reactor protection system is it's also a power supply. So we have power and logic in this system that provides our safety function for our reactor. So once again, reactor protection system is not a fission product barrier. It's a thing that we use to make the scram happen. All right, so I'm looking at your quiz. Most people did good on actuation and interlock. Emergency action levels. I'm undecided. I haven't finished your final exam, by the way. Spoiler alert. I'm still working on some of these questions and trying to decide exactly what I want to ask. What I'm noodling on right now is how important is it for you as a college student to truly be able to specifically define each of our action levels? I don't know. I think it's important that you know that there's 4. I think it's important that you know what they are. I think it's important that you understand that some of them don't require any off-site action and some of them do. And I think it's important that you understand at what point are we saying the site needs to be evacuated and what point are we saying the public needs to be evacuated. Because that's the perspective that you're going to need to sort through. We talked about a little bit of fake news stuff, right? The dihydrogen monoxide parity. You're going to someday see something on the news. Columbia Generating Station has this declared an unusual event. And you will know, well, okay, understand something happened, no real concerns. And then what about the next level? What about the next level? So make sure you review what those levels are and what order they are and which ones would be important to understand from a public perspective. I think that's how I'm going to write that. All right, logic channels. Let's see. How do we want to do logic channels? All right, I have thought about it. Here's what I'm going to do for logic circuits, logic channels. The 1 of 2 taken twice, 2 of 2 taken once, 2 of 3 taken twice, whatever. What's important? What do you need to understand? Do you need to be able to nuke out whether an actuation occurred based on whatever? Eventually, yeah, you're going to need to look at a print, right, with the circuits like you've seen in your text, and determine if this contact closes and this contact closes, does this relay cause an actuation or not? Do I need 2 relays to actuate? Do I need 2 contacts to close? What I think is important for you at this point is knowing that we have these logic systems, knowing the idea of redundancy, understanding how contacts and relays work together, and how these logic systems prevent inadvertent actuations, how they make sure that we really have a problem so that we don't inadvertently just trip the reactor every 4 days. Don't worry too much about a specific noodle out what type of logic it is question. Expect a question that covers a bigger perspective idea on what these logic systems are designed to do. I was looking at your text, and I am right now. I would know coincidence and redundancy. I would know failsafe. Now failsafe, some of you had a problem with failsafe too. If you look at page 9 on your text, under failsafe features, paragraph delta, it says the opening of the contacts to a relay, which initiates a scram, is what a failsafe circuit is. That is, power, the RPS system, the reactor protection system, the power side of the RPS system, holds those contacts closed under normal conditions. Because if we have a complete loss of all AC and DC power, we don't want to lose our ability to monitor our logic circuit and not have a scram if something happens. So if we lose all power, we want it to fail in a safe condition. If those contacts lose power, those contacts open, which then de-energizes the relay, which then causes the scram. So it's designed to fail in a safe condition on loss of power. And then of course we have some backups to that, because even if that failsafe fails, we have other ways to take the reactor in a safe condition. Our backup scram valves, we have safety relief valves to relieve pressure, we have containment isolation valves that all go closed to bottle everything up. Lots of different stuff. Like I said, I'm not going to give you here's a logic circuit, which one of these types of logic is it? I think that's beyond the scope of what you need to do. All right, let's scroll down here to, I'm going to jump ahead to the mitigation of core damage and accident management. There were more struggles than I expected with the idea of these heat sources, sensible heat and decay heat. So let's talk about sensible heat. Sensible heat, I think, is intuitive to all of you. I didn't see anybody really struggle with that. It's the idea of I take my coffee out of the microwave and I hold my cup, it's full of sensible heat. It's the heat that's retained after the heat generation has stopped. When the microwave turns off and I pull this out, this is hot. And that sensible heat, it's losing that sensible heat. That sensible heat will decay away, which is where I think some people get a little tripped up, right? It gives off some of its energy, but it's heat, but there's nothing that is continuing to add energy to this cup at this point, right? Sensible heat is where nothing is adding to that energy. Now, that heat that's retained is either being retained in a perfectly insulated condition or slowly being given off to its surrounding environment. Decay heat. So on that graph in your text, it shows decay heat on a reactor shutdown starting off at about 6% reactor power. And then it decays off, right? Where it trails off after 100 days 100 days, 200 days. That's where decay heat is actually now really becoming sensible heat. Decay heat at that first initial, so you have to think about how fission works again. All this moderated water around the fuel is thermalizing these neutrons, right? Slowing those billiard balls down until they can be absorbed by the uranium. When we insert a control rod, right, a boron, hafnium control rod, all we're doing is we're putting big neutron sponges inside all that fuel. These neutron sponges absorb all of those, not all, and that's decay heat, is the fact that those neutron absorbers don't absorb all, but they absorb a bunch of those free neutrons that are bouncing around being thermalized and getting absorbed. However, you've got a neutron from a fuel pellet that goes to the coolant channel, gets thermalized, and happens to get bounced back into the fuel and then fissions again. Fission still happens. Fission is still going on a reactor scram when the rods have been inserted and the reactor, what we call, shut down. In fact, once fuel has been irradiated and exposed to thermal neutrons, fission is always happening. That's why I gave you that example of the Oslo reactor, because that fission goes on for forever, right? It's a subcritical reaction, so it gets less and less and less and less. That reaction starts to drop off, right? Because it loses its moderator, and that it's not a self-sustaining reaction. Every neutron population, every life cycle, you get fewer neutrons and fewer neutrons and fewer neutrons. That's what decay heat's talking about. When those rods go in, we still have fission occurring at about 6% reactor power. Now it's so subcritical that it starts to drop off fast. That neutron population starts to die off. That decay heat is still fission. Food break. I'm hungry. All right. Be like Brad Pitt and just have some snacks on set. Next one, conduction, convection, modes of heat transfer. I think it's been clear that for modes of heat transfer in a nuclear reactor, I really don't care about the third one, right? The radiation. Radiation is a little more ambiguous. There's a lot of stuff in here about the mechanism, and it even says in the last paragraph that during a LOCA, a loss of coolant accident, when the fuel rods become uncovered, conduction and convection heat transfer rates drop to near zero due to the low thermal conductivity of the steam, setup, a bunch of stuff, right? Radiation heat becomes significant. Yeah, when compared to the conduction to the air and then the convection through the air and the steam that's happening, the radiation is going to be a larger scope of it. Don't care, right? At that point, doesn't matter. What I care that you care about, is how heat is transferred in the core. And that's conduction and convection. And understanding where one stops and one starts and where they blend, right? So conduction, what does your text say? It says molecule to molecule, right? Yeah, one molecule to another. Kinetic energy is transferred by collisions between the adjacent molecules. Yeah, we'll go back to the coffee cup. When I heat my coffee up, which I'm getting really low on, that heat in the coffee is being transferred to the cup, right? The cup is absorbing that energy given off from those molecules, and it's equal. They're trying to equalize, right? One's getting hotter, one's getting cooler, and that's conduction, molecule to molecule. Now within the coffee, if this was a full cup of coffee, there would be the mechanism of convection going on, because heat rises, and that's when we say heat rises, we're really saying that things that are hotter, fluids that are hotter than another fluid, or one part of a fluid that's hotter than another part of a fluid, is less dense. And that lower density rises to the top, right? Because the denser is more affected by gravity, it goes down lower. You see that in, I was going to say you see it in the ocean, and then I remembered, well, except for when you don't, right? I was in submarines for 20 years, and one of the things this is just a cool side story. One of the things submarines do to hide is we look for thermal stratification layers, where a cold pocket or a warm pocket of water, because of how it's moving, because it's a current, because it's moving faster than the surrounding water, and it develops a stratification layer, is a different temperature than the water above and below it. And it doesn't matter whether it's cooler or warmer, as long as it's different, we can hunt out those changes, those stratification layers. And if a submarine gets into this stratification layer and you got 200 feet of water above you and the rest of the ocean below you, and you're in this 100-foot tall stratification layer that's a different temperature because it's current, the sound you generate gets bounced off of that boundary, that temperature boundary, because of the density differences. And so the sound you generate will go through that stratification layer. But if the Russian fishing trawler sitting up on the water with a microphone in the water is looking for you, and you're in that thermal stratification layer, they won't hear you. Anyway, that was a side story. Usually heat rises, which forces cooler stuff below. Where was I? So your text has some very specific stuff, right? Conductivity materials expressed as K. Units are the BTUs per hour, per hour, foot, degree Fahrenheit. Yeah, you don't memorize those numbers. Please don't. Please don't. You just have to understand the concept that, in fact, the material makeup and the size of the surface changes how fast or slow heat is transferred through a material. And that's the thermal conductivity. Some things are better than others, and it talks about metals are usually very good. Ceramics, not so good. Gases, not so good. But being able to describe and even draw out how heat is transferred from the center of a fuel pellet through the material, right, molecule to molecule, through the cladding to the water, how that conduction happens, and then once it's in the water, that steam bit turns that little bit of those molecules of water to steam, and that little steam bubble gets carried through the current to the coolant, right? At some point we're now talking about convection. So let's go down to the convection. Yeah, flow past a heated surface, right? The cladding, fuel pellets, fuel cladding, and the coolant going past the surface. The coolant is carrying away that heat. That's the convection. Now sometimes we have forced convection because we have these big recirc pumps that are driving this flow through the core. And then sometimes, another submarine story, sometimes you don't want to run a pump. So my first submarine had the ability to shut down our recirc pumps and cruise along with the reactor at power without the pumps running, so we're super ultra quiet through natural convection. So the water going through the fuel gets hot, and as it gets hot at lower density, rises to the top, right? It also turns to steam, boils off, and then and it was a different type of reactor than what we have here. Here we're talking about, here at Columbia Energy, we have a boiling water reactor. On submarines and aircraft carriers, they use the pressurized water reactors. So the primary coolant loop is all contained. So it goes through the steam generator and then condenses and goes back through the core again. Anyway, so that density difference drives that coolant flow to remove the heat from the reactor. And that's natural convection. So you can either have to turn your recirc pumps on, forced convection. Turn the recirc pumps off, natural convection. Another example I'd consider is solar systems. If any of you or your parents, I guess, have solar systems, some of them used forced circulation, forced convection. Some of them use natural convection or natural circulation, where the heat drives the flow. So as the water or whatever medium, their alcohol, whatever they're using to heat the sun to heat up, gets hotter, it goes up, right? And that creates a pressure at the top, which forces flow in through the bottom and drives more of that whatever fluid it is in, and then it just keeps circling through. All right, adequate core cooling. So adequate core cooling. On page 28 of your text, we start talking about core cooling methods. The number one is core submergence. That is always our number one goal. Keep the core covered with water. These other ones are only in the event of an accident. Something has happened and we've had to shut down the reactor. We've lost our high pressure feed injection. Something else has happened and it's causing us to lose level. And as that level goes down, we understand that we still have cooling. Now we have to describe that mechanism of cooling, because it's not just submergence. So steam cooling. So as long as we have some injection going in, steam, though it's a poor conductor, right? We talked about conduction methods, convection, what is a good conductor, what's not. Steam is not a good conductor heat, but it does conduct heat. It does carry away heat. So that steam carrying away some heat does provide cooling. The steam cooling without injection, yeah, so we're not able to get any water in. And that would be tough to do. Like, that's seriously tough to do. We have so many injection systems, it's ridiculous. But let's say we lost all our injection systems. There is so much water in that coolant system still that we can sustain a cooling for a long time just from that boiling off. So once again, it's using the steam and it's just saying, hey, I'm using the steam to remove the heat, but now I don't have any makeup injection, right? That's all that's saying. Spray cooling. We have a couple of spray cooling systems that are designed differently. So we have some feed water injection systems that inject water into what we call the downcomer region. So it's all submerged, it's all underwater. And that's just adding water to water, right? But we have a couple of spray cooling systems that inject water into the core from the top, well, one from the middle and one from the top, that sprays it out in droplets, right? Now that is a highly effective way of suppressing a large amount of heat generation. Because all those droplets, you're giving a lot more surface area to the heat in a rapid manner, and so it collapses that steam bubble. It reduces an immediate reduction in that heat. It's very, very effective. And that's the spray cooling. So you still have to have some water. You have to do some of the fuel has to be covered for this spray cooling to be effective, because that's also your source of the water. It's kind of recirculating. That's going through the spray cooling. But no matter what you have, whether you have core submergence or you don't, and you have spray cooling with or without injection, steam cooling with or without injection, or you have spray cooling, all four of those are methods of adequate core cooling, which you will need to know and understand. And which one is our primary goal? Which one are we normally crediting? All right, we talked a little bit about core damage, right? With the fuel pellet, the cladding, anything that causes the release of fission products to the coolant, fuel, that's core damage. You all did very well on the hydrogen Zirk water reactions, the steel steam, the core concrete, radiolytic decomposition. And the one I really, the one I would, you're gonna get something on this. The one I would focus on is the the zirconium steam reaction, or the metal water reaction. That is the one that is the biggest, or it was a big concern at Fukushima. That's the one that caused a little bit of problem, right? And I'll save the other story for later. But that's the mechanism I would study. I wouldn't worry so much about the steel steam or the core concrete or the radiolytic decomposition. Focus on the metal water reaction, including the equation, the temperatures, and the equation, the temperatures, the mechanism, what's happening, and why it's bad. Know why it's bad. If you look down to page 32 and 33, it talks about potential hazards from hydrogen. That's part of the why is it bad, why it's bad. You all did really good on the parameter monitor. What do we monitor? What kind of parameters do we monitor after an accident? I think that's all self-explanatory. We want to know how much water's in there. We want to know how much inventory we have. We want to know what temperature is, pressures, all these different things. Yeah, that makes sense. If you see something, I think you'll do fine already on it. Radiation monitoring response, yeah. Okay, tagging. Yeah. There were more struggles here than I expected. Danger tags. Danger tags, right? Danger. Danger tags are red tags put on a thing that says, you can't touch this. You cannot move, reposition, don't even freaking breathe on it for very long. I'm joking about the last part, but you know what I mean? So the question I gave you, probably a little tricky because I put you in a couple of different situations where you're probably at jobs where you're used to, well, yeah, I can't do that unless my supervisor says, right? So the idea of that question was to show you, yeah, even in the industrial world with the lockout tagout program, nobody can violate that. It is incredibly illegal to operate a danger tag component, and nobody can come and say it's okay. They can't do it. So know what a danger tag is designed to protect you from, and I think y'all did very well on that. But realize that you can't actually reposition the thing. You can't push the button, you can't turn the switch, you can't flip the lever, you can't open the valve, you can't plug it in, you can't do anything. Whatever that danger tag is designed to prevent, you can't do until that danger tag is cleared. The other one, I was hoping to see a little more information on. And I may have had a little bit of an assumption on what knowledge you're coming into this with. So let's talk about a live, dead, live check. Okay, a live, dead, live check. If you think about this is an absolutely overdone, ridiculously overdone precaution. This saves lives. I have a voltmeter. If I was smart, I'd have had a voltmeter sitting here, but I don't. I have my coffee. I got my phone. I got my voltmeter, right? And I take the leads, and I'm going to work on this computer here, right? But I want to make sure it's dead. Well, if I hook the voltmeter up to the computer, and my voltmeter says, yeah, the computer's not energized, it doesn't have power. How do I know that the voltmeter's working? So what we do is to verify that the voltmeter's actually working, we test the voltmeter on a live circuit of the same rating. So if this is 110 volt AC, I'm going to test my voltmeter on a live 110 volt AC circuit. Okay, I plug it in. Oh yeah, that circuit is live and my voltmeter shows the 110 volt AC. It's working. I unplug it, then I plug it into my computer and it says 0 volts. Okay, Now I know it's de-energized, maybe. So we've done the live dead part. The reason we do a live dead live is to verify that in that moment of time, from testing on the live circuit to testing on the dead circuit, the voltmeter didn't just suddenly break. So then I take my leads out of the dead de-energized equipment and I plug it back into my live circuit and verify that the voltmeter is still working. If the voltmeter says, oh yeah, 110 volts AC, now I know that the voltmeter read 110 volts AC on a 110 volt AC circuit, then read 0 on the thing I'm about to put my fingers in and work on, and then read 110 volts AC again on the live thing. That's a live dead live check. That is critical to understand in the industrial environment, not just nuclear. If you have electricians or wherever you work that aren't doing that before they work on a panel, all right. Peer checks. So a peer check. There's lots of different ways of controls. You read in here that we have lots of different ways of making sure the right things are happening. We have concurrent verifications. You can have what people would call a second check. Hey, I just went and flipped that switch. It's in this position. Will you check and make sure I didn't look at it wrong? Yep. Then they check it. That's not a peer check. What you need to understand about a peer check and why it's so important in the nuclear world is that we can't often risk having a mispositioned component, right? If I go open a valve, or think I opened a valve, and then I send somebody after to check, hey, can you make sure I open that valve right? And then they check and they're like, dude, you closed it. I'm like, oh, that sucks. That's concurrent verification, or that's not even concurrent verification, that's post verification. But that's a verification of the process after. That's the second check. What if me putting that valve in the wrong position caused the plant to scram or a loss of coolant accident or something else, right? The way you want to do things in the nuclear world is, hey, I'm about to turn this valve, I'm going to put my finger on the valve in this direction, and I expect to see this response. Do you agree? And their peer checker will say, yeah, I agree that that's the right valve, I agree that that's the right direction, and I agree that that's the appropriate system response. And then I take that action. That's a peer check. You need to understand that a peer check is before the action is taken. And why? Why? The consequence. I would, hint, hint, I would pay attention to why would we want a peer check versus a second check. All right, so there's a lot of learning objectives in your text. There's a lot of things we didn't cover in this review. I don't know how long this is going to end up being, but I'm going to do a lot of editing. There's a lot of this footage you're not going to see. But those are some of the highlights of some of the weaker things I think you've seen. Maybe some of the ideas you've struggled with. What you need to do on your final exam, there's not going to be as many multiple choice, right? I'm not going to do a lot of that work for you. I'm actually making my job harder on the grading end of this because I've got to go through and read every answer for however many questions. Doesn't matter. You're going to do more typing on this one than you have on the others. And that's because I need you to demonstrate an understanding of the concepts. Not just, I knew where to find this in the text, right? I'm definitely going to be looking for and checking for copy and pastes. Don't do that. There's going to be a lot of similar words. You can't get around that, right? Only so many ways you can describe a peer check. I don't want you inventing new words. So appropriately describe the concept. Just don't copy and paste, okay? Put things into your own words. Bring in other ideas. Go beyond what's in the text. Go talk about 3 Mile Island, Davis-Besse, Chernobyl, Fukushima, whatever ones, SL1, these other secondary ones that you researched. Bring in those ideas. I mean, really, this whole course is talking of, is this the culmination of all this stuff we've done is nuclear safety, right? Major industrial operating experience. How do we keep ourselves safe? What have we learned? And so showing those examples, you doing that in your answers is all I'm looking for. I think that's it for my notes. I haven't seen any questions pop up on the discussion posts lately. There's still 1 week left, right? Today is, I don't even know what today is. Sunday. So your final exam will be due midnight next Sunday, a week from today. If there is anything in here you still don't understand, shoot me an email, put it on the announcements, create a discussion post, put a reply on one of the other discussion posts, something, okay? I generally check these every day. I'm working Tuesday through Friday from 1 p.m. to midnight right now. So if you're posting anything in that dead time, I'm not going to be able to respond. But as soon as I can get to it, I will. Okay? Finally, as I've done on a couple of your quizzes, there's the last question on here, which will be free points as long as you answer. And I know on that Mod 4 quiz, somebody didn't answer that last question. And it's free points, right? I don't care what you put in there. Hey, Jason, this felt like a self-study course and whatever, right? Okay. Yep, I appreciate the feedback. So give me something, put something down there. But I want to know if you were to sit through this again, next, summer, fall, winter, next year, whatever, if for whatever reason you were going to do this course again, what would you want to see different? Tell me what you want to see the same. What did you like? What didn't you like? That critical feedback. Some of you I see are on my course, the fluid power systems. It's going to be a little different than what we've done here because this is more conceptual in nature, whereas fluid power systems are, or some math, some engineering. That's going to look different, but I still want to bring some of these ideas into that. So I look forward to seeing how you do on your final exams, and this is my last plug for your assignments. Get those assignments done. There's some of you that I think have some assignments that you haven't done just because you may not realize you haven't done them because you've done everything else except for that one for some reason. So everybody go back in, look at your grade tab and look for anything that has a 0 or a dash. If it has a dash or a 0, it means you haven't done it. Because I've given you a grade for everything that you've turned in, submitted, emailed me on. However you need to give me the answers, I will, yeah. And make sure if you haven't gone through and read all my feedback on any of your questions, go through all those assignments and check the feedback. Some of those, especially Mod 4, hey, you didn't answer question number 1. Was that intentional? I don't know. Did you not know the answer and just left it blank? Or whatever the reason, go back in. If you put in comments, put in a reply, shoot me an email. Hey, I didn't answer question number 9. I didn't answer question number 1. Here's my answer. I will update your scores, okay? Up through midnight Sunday. I have a little grace period after midnight Sunday to get your grades finalized. So I want to give you every opportunity to do that, to update your information, make sure it's all accurate, and then I'll finalize your grades. So just because an assignment's been done and turned in doesn't mean that's your grade right now. Well, that's all I've got for your final exam review. Anyway, this is fun. Once again, I apologize for this is the first time that we've met. I know I tossed out an idea early on about, hey, let's do some kind of cruise or whatever. And only one of you responded, so I dropped that idea. Even though I kind of wanted to show off my pretty car. I'll put a picture on here of it. But yeah, maybe next, for those of you that are following me into the 170 for the fluid power systems, maybe we'll have an opportunity to have a little more personal interaction. Either way, so far,
I don't understand.
Huh. Well, I don't understand either, Google. Either way, it's been fun. I've really enjoyed this course. I've really enjoyed working with you. I hope you've learned something. So, take care. Want to lose our ability to monitor our logic circuit and not have a scram if something happens. So if we lose all power, we want it to fail in a safe condition. If those contacts lose power, those contacts open, which then de-energizes the relay. De-energizes the relay, which then causes the scram. So